In this video, in the next couple of videos, I would like to discuss area and arc length in polar coordinate. At this point, you should know how to graph, for example, a polar equation r equals to 8 times sine of 2 theta. The graph in a polar graph, that the graph of this equation r equals to 8 times sine of 2 theta, that looks like a flower. So we have one petal, 2 petals, 3 petals, and 4 petals. So we have a polar equation and then we have a graph. And then to find the area, I am interested in finding the area of one petal, and then since they are symmetrical, I can find the area of one petal and then multiply by 4. How to do it? To do that, we need to set up an integral. And then other than that, we have a curve. I would like to find the length of this curve. So arc area and arc length all in polar coordinate. And then starting from the area, like I said, we need to set up an integral to find the area. Just like when you study area under a curve, the fundamental theorem of calculus, you can set up a definite integral to find the area under a curve. And then when you study area between curves, you need to study how to set up an integral. The volume, the shell method, you need to know how to set up an integral. Okay, so this, I will show you how to set up an integral. And then in this video, I am not going to do an example because each example that takes a lot of steps. So in the next couple videos, I will show you a few great examples. The problem is long, you have to do integration, but the process is a lot of fun. Okay, let's get started. Okay, starting with turning to the basic area of a circle, that is A equals to pi r squared. No question with that. Everybody knows this formula. That is the area of a full circle. And then what about area of a sector? What is area of a sector? Area of a sector is, what if I only want a piece of the entire circle, and then the area formula is 1/2 times pi r squared. How do they get that? Here is how. So let's say when theta is equals to 1 degree. This 1 degree refers to 1 degree out of the entire circle, which is 360 degrees. And then the area is equals to pi r squared. That is a full circle, but we are looking for 1 degree out of 360 degrees. And then when theta is equals to pi over 2, so pi over 2, this is in radian, and then I have A equals to pi r squared, and then multiply a pi over 2 divided by 2 pi. This is in radian. Pi over 2, simplify that, and then the pi's got cancelled, but we do have another pi. Then we have a 1 over 4 pi r squared. Okay, so that means when theta is in radian, I have A equals to pi r squared, and then multiply the theta divided by 2 pi, and then simplify that. What can we do? We have a 1/2. The pi got cancelled. We have a theta. We have a r squared. So that's how we get the 1/2 times theta times r squared. Okay, let's try to use this. For example, let's say I have a circle. Radius is equals to 4, and then theta is equals to pi over 2. What's the area? There are two different ways to do it. The first way is you follow this formula, 1/2 times theta, and then times r squared. That is equals to 4 pi, and then area of a sector. How much? How big is this? How big is this? Pi over 2. Pi over 2, that means that is 90 degrees. So that is exactly 1/4 of a circle. Okay, speaking of 1/4 of a circle, I can do the following. A equals to pi r squared first of all. And then that is a pi times 4 squared. That is equals to 16 pi. This is a full circle, area of a full circle. Since you only want 1/4 of it, okay, then 1/4 times 16 pi, that is equals to 4 pi. That is equals to 4 pi, and then pi over 2, this is 1/4 of a circle. Okay, then that is regarding area. And then for the arc length, let's do arc length. Okay, how about I will move this to a side, and then arc length of a circle. Then let me draw a circle. So I'm going to draw a circle, and then center, radius, and then radius. And then that gives me theta. And then arc length refers to this length. How do we find this length? When theta is in degree, the arc length they use as is equals to 2 pi r, and then you multiply 2 pi r. What is 2 pi r? 2 pi r is the circumference. That means the length of the entire circle. Are we taking the entire circle? No, we are not. We only need to take something out of 360 degree, and then that is in theta. And then when theta is in radian, I will do S equals to 2 pi r. That is the circumference, the entire circle. We are not taking the entire circle. That means out of the whole circle, 2 pi, we only take theta of it. So simplify that. That is equals to theta r. Okay, theta r. So that is the arc length formula. Okay, and then returning to a polar equation, how do we express a polar equation? You can say r equals to, let's say r equals to a times sine of 2 theta, r equals to 7 times cosine theta. That is a polar equation. Or you can write f of theta. A polar equation on a polar plane. And then back to a rectangular function, you can state the domain, right? Where x is between a and b. In polar, we use alpha and beta. The theta is between alpha and beta. And then let's say that is the graph. This is the graph of f of theta or r. So we sketch the graph of a polar equation. And then in the origin, we don't call this origin. We call this a pole. Back to the polar plane. Back to a polar plane. And then this one, we call this a polar axis. Just some names that you have to know. What about between the angle between alpha and beta? You also need to refer to your polar plane. So we use polar plane in the previous video. I give you a polar equation. You sketch the graph for me. The polar plane refers to the graphing paper. The alpha and beta on the graph, that refers to this line. So alpha is right here, and then beta is right there. So we have an area, the alpha and beta. So we make two cut to cut a piece of area, and then we need to find this area. So I want you to find this area. We need to set up an integral to do it. And then the alpha and beta, let's introduce another name. That is, they are called radial line. Radial line. This line is called radial line. You have a polar equation, you sketch the graph of it, and then you make two cut, and then you cut some area, and then you need to find area. To find this area, we need to set up a definite integral. How do we find the area? Okay, here is how. Let me just give you that. So we have r equals to f of theta. We call this a polar equation. Okay, no question with that. And what is the area? The area is equals to what? You have 1/2 and then times integral from alpha to beta. Alpha to beta means from a to b. And then you square the function, d theta. You square the function. And then this is derived from the area of a sector. A equals to 1/2 theta times r squared. So I am giving you the the integral right now. So you need to know what the function is. So because you have a polar equation, then you have a graph, right? Okay, then you square that polar equation. That will be your radicand. And then you have integral from a to b. There is a 1/2 outside. Okay, let's get to this formula. I'm going to do it step by step. Okay, then this one, I am going to move this, and then allow me to move this up. I already prepared this one because that will just make the whole explanation much smoother, because this graph is hard to talk and write and make it nice at the same time. Okay, let me explain what is going on. You can feel free to pause the video at any time, write these notes on your paper, and then you can continue. You have a green curve. The green curve represents f of theta. So you have f of theta, and then you sketch the graph of it, and then you have two radial lines. I am looking for the area that is cut between alpha and beta, and then you are looking for this area. And then do you remember that when you study area under a graph, the very first method you study is not go ahead and integrate. The first method you study is you drew triangles, right? You drew triangles under the graph. You study the left sum, the right sum, the midpoint sum. This one we use a very similar concept. From beta to alpha, I will pick a point on the polar graph, and then I go ahead draw. This one is not really a triangle. This one becomes this one is a rectangle. And then you pick another point on the curve, and then you extend forward, and then you connect that to the pole. Pick another point, extend forward, and then you connect it to the pole. And then how much do we have to go? That is really like the width. Okay, and then use triangle approximation, divide this area into n subintervals. So in this is similar to what you studied in the past, left sum, right sum, midpoint sum. We use beta minus alpha divided by n intervals, and then that is the delta theta, the angle. And then as angle increases, theta increases as theta rotates counterclockwise. Back to your unit circle. This is a 0 degree, and then as you rotate counterclockwise, you will reach to 90 degree. That's why I said as the theta rotates counterclockwise, and then the value of the theta is increasing. Just think about 0 degree, and then you have a pi over 6, and then you have a pi over 4, pi over 3, and then a pi. So this will be a 0, 30, 45, 60, and then 90. So as you rotate, as the theta rotates counterclockwise, the value of the theta is increasing. And then I cut a piece of the triangle, and then this width is the delta theta. Oh, just like two. This is hard to read. The change of theta. How about this? We don't call that delta theta. We call this the change of theta, the change of angle. And then this one is definitely the that looks like the radius r. And then also between alpha and beta, I will say as the angle, because every time you put a point, there is an angle, right? From the origin, from the polar axis to this point. You know how the polar graph works. From the polar axis to this point, there is an angle, and then that is how we line them up between alpha and beta. The theta 0 is the smallest. That will be you can imagine that will be a 0. The best way to think about this is this one. How about this? This one, I will just pick a 0, and then a pi over 6, pi over 4, pi over 3, and then eventually you will reach to beta. How's that? This should be easier to interpret. And then how is that related to that integral written on the previous page? So let me state that formula again. Area of a sector. Area of a sector. That is A equals to 1/2 theta multiply r squared. And then R is equals to f of theta. Okay, R is equals to f of theta because Okay, this word you can think about that as the radius. Then if you think about that as a radius, then the green curve, I would imagine that that would be a circle. But R is really the R equals to f of theta. Because when you select a theta value, when you select, let's say, a pi over 3, when you select pi over 3, you plug it in. When you select pi over 3, so pi over 3 on the graphing paper, pi over 3 is like right here. You plug it into the function, then that gives you a point. Okay, you select an angle, you plug it into the polar equation, that gives you a point. That point is on the curve. Okay, back to our writing. R equals to f of theta because R is different at different theta. So that's why we need to go over the table values. You have a polar equation. You plug in different angle to the polar equation, then you get a different R. That's why you get different points. And then we have so many triangles. We want to sum up the area. So sum up the area of n triangles to get total area. And then the total area is equals to limit as n approaches to infinity. Hey, how about we write the limit in blue? The limit as n approaches to infinity. Just like the left sum, right sum, and midpoint sum. For the rectangle, the more rectangle you use, the better approximation you will get. N approaches to infinity, I will just sum up. Sum means we need to use a sigma. I goes from 1 to infinity. Oh, I goes from 1 to n because n approaches to infinity. And then we have a 1/2 f of theta and then square. 1/2 f of theta square and then times the change of theta. We need to sum up n of them. We need to sum up n of them. How do we get the change of theta? The change of theta comes from here. This theta is now the change of theta, which is here. Is here. And then this is this one you can think about that as actually the R is here. Oh, you can, all you need to do is we follow this. Okay, let me just give you a highlight. R square, R is equals to this, and then you have this, R square, and then this square, I should use, how about this color? This square is there. 1/2 R square, and then times the change of angle. And then continue, the R equals to f of theta. Oh, I should go back to a pen. R equals to f of theta. That is the value of R. Depends on independent variable. Independent. Theta. Okay, every time you have a different angle, you plug it into the equation, then you get a different R. So you have 1/2 times that R square times the angle that gives you the area of one triangle. How many triangles do you have? You have infinitely many of them, then you add them up. So you add them up as n approaches to infinity, we can write the following. A is equals to integral alpha theta. Oh, this is so hard to read. The angle goes from alpha to beta, and then I have 1/2 the square of the polar equation, and then times d theta. That's how we get the formula. So this is only for finding area. for finding area. And then regarding the arc length, we will get to that. So now we know how to set up the integral. You might think this is easy. Oh, I see a problem. I see the problem. I plug in alpha and beta to the integral. They must give me the polar equation. Okay, all I need to do is just put everything in and then integrate. It is just that easy? No. When you solve a problem, the problem often provide the polar equation only. Okay, then you get the polar equation. You can plug in the polar equation to decimal to see the graph. But regarding the alpha and beta, finding that isn't easy. I will show you a technique to find it using decimal. Using decimal, that will be very convenient. But if you just graph everything by hand, point by point, that will take a very long time. How about this? We discuss that in the next video.